Stuff from today's notes will be on electromagnetic induction. Okay, we will have an assignment today, 1202.4, electromagnetic induction problem set, and that is going to be the last topic prior to your quiz tomorrow. So before we get into the notes, let's go ahead and go over the warm-up. So number 1 on today's warm-up says, what magnetic force acts on magnet A due to B? Okay, so I'm not looking for a number here. In fact, we didn't get any numbers to begin with, and we also haven't calculated magnetic force, and we won't be doing that. Instead, I just want you to tell me whether it is attractive or repulsive. And so if you take a look at this diagram, these magnets appear to be floating one on top of the other. And you could do this. You could grab a rod or a pencil and get some ring magnets and put them on there. And if you put them on there correctly, you can make them look like they're floating. Okay, but the fact that they look like they're floating, what does that tell me? Are they attracting or repelling? Repelling. So number 1 is it is a repulsive force. They're repelling each other. Number 2. Describe the gravitational force on magnet A due to magnet B. Again, gravitational forces exist between any two objects with mass. Magnets have mass. Therefore, magnets do experience gravitational forces. Gravity is only ever attractive. It is not possible to repel something gravitationally. So that means that although these magnets are repelling magnetically, they are attracting gravitationally. That also tells me that that gravitational force must be quite a bit weaker because they're still floating. Okay, so the forces aren't the same strength, but the gravitational force is an attractive one. That's number 2. Number 3, if magnets A and B are electrically neutral, describe the electric force on magnet A due to magnet B. The electric force or electrostatic force is the third field force that we talked about, and that force is going to exist due to a charge imbalance between two objects. That could mean that you have two objects that have both have a negative charge because they both have excess electrons. It could mean that you have one object that has a negative charge and one object that has a positive charge because one of them lost electrons and the other one gained it. But in this case, it says that they're electrically neutral. And if they are both neutral, okay, then that means that there is no electrostatic force of attraction or repulsion. Okay, so if they're neutral, they're not attracting or repelling. Okay, so that last one should be that there is no electric force acting on them. Yes?
What slide number is that?
I am on slide 65. All right. So again, guys, please make sure you have answered today's warm-up question. And again, we're about to get into our last day of notes. So if you don't have out a notebook, get one out so that you can write this stuff down. And if you got a phone out, let's get those put away so that you can, again, listen up and write down some notes. All right, so we already know that moving electrical charges, that's a current, will generate a magnetic field. We've already looked at things just like this, where you have this field that's generated around a current-carrying wire. But today we're going to ask the opposite question. Can we use a magnetic field to generate electric current? Is the opposite statement also possible? Okay, and the answer to that is yes. Okay, and you should already know that because on Monday of this week, you guys were assigned a simulation with the substitute, and you actually already did this. So we're going to be talking about some of the things that you saw when you did that simulation. But in that simulation, you were able to move a magnet into and out of a coil of wire and cause a light bulb to light. That was on the FET. Okay, on the gizmo, you did something similar by moving it or rotating it, but it was the same idea. Okay, and so yes, you can use a magnetic field to induce an electric current, and that is called electromagnetic induction. So this is the title of today's notes. It is also the first definition I'm going to give you. Okay, so again, add this to your notes. Electromagnetic or magnetic induction is the production of voltage across an electrical conductor in a changing magnetic field. Basically, we can use a magnetic field to make electricity flow by changing or moving the magnetic field. And again, that's exactly what you saw in the simulations. You saw that moving a magnet into or out of a coil of wire by changing the field that went through that wire, you were able to cause current to flow. You saw that by rotating a loop of wire in a field, you were able to cause current to flow, or by moving the loop toward the magnet. Okay, there were different things that you tested in those simulations. If you haven't done them yet, you absolutely need to, and again, that was the assignment from Monday. Okay, but again, that's electromagnetic induction. So this video clip is going to show a real-world example of what you did in the FET. He's going to take a magnet and he's going to move it into these different loops of wire, and he has different number of loops on each one. And you're going to look at what happens to the current flow just by putting a magnet in there. There's no battery here. It's just a magnet and a loop of wire. And so watch this video clip. We'll talk about it again in a second, but this is electromagnetic induction.
This is a demonstration of Faraday's law of induction. I hope you remember this demonstration because it's a very important one in the history of physics. What it demonstrates is that a changing magnetic flux through a coil of wire produces an EMF, namely a voltage, in that coil of wire and a current in the coil of wire. This is not something that people come across every day, but it's the basic principle behind generators, the alternator in your car, etc. So we can generate electricity by changing the magnetic flux, the amount of magnetic field that penetrates a coil. So what I have here are three separate coils of wire, one with very few windings, one with about double the number of windings, and one with approximately quadruple the original number of windings of wire in this coil. I also have and this is a galvanometer. It just measures the amount of current in the wire, in the coil. I also have a magnet, North Pole and South Pole. I'm going to be inserting the magnet into each of these three coils of wire, and we'll be watching the black needle here in order to demonstrate the presence of a current in these wire loops. So starting with the small one, if I move the magnet into the wire loop, you saw that as the magnet was moving into the wire loop, the needle bumped up positive. But now the needle isn't moving at all. And this is a very important bit of Faraday's law. There's only a current when there's a change in the magnetic flux. It doesn't care how much magnetic flux there is through the coil. Right now there's a lot. All that magnetic field is through the loop. What matters is when it's changing. So now I'm going to pull the magnet out of the coil. And what you see is that while the magnet was leaving the coil of wire, the current was negative. So we had an opposite effect. And we'll talk a lot more about that. The effect is proportional to the number of windings in the loop of wire. So we should see a bigger effect through this loop and finally for the third loop. So we definitely saw a bigger current, went all the way to the maximum and minimum, and then I think we actually pegged out here. It went beyond the maximum this galvanometer will measure. But again, a changing magnetic flux in a loop of wire causes a current in the wire, and that's Faraday's law of induction.
Okay, so that's pretty much what you did in the FET. Okay, you were able to move a magnet into a coil of wire, and you saw current flow one way, or a light bulb light, and then you pulled it out and the current flowed the other way and the light bulb lit again. but it's all about a changing magnetic field. You'll notice when he just put the magnet in and left it there and it wasn't moving, then nothing happened at all. So they have to move with respect to one another. Whenever we're talking about electromagnetic induction, it's the changing field that is going to cause that electromotive force that's going to create that current. And so that's what it says here. Again, this is kind of summarizing the things that we just talked about, or that he just talked about in the video. But a changing magnetic field will induce an electromotive force, or EMF, in a loop of wire. This could result from changing the magnetic field strength. I'll show you an example of that in just a second, but it's also if you have a magnet that's closer and you're moving it, or farther away and you're moving it, obviously your field strength is going to be stronger if the magnet's closer, because the field lines are going to be closer together. As you move it farther away, we know those field lines get farther apart. So you could also think of it like that. But that's also kind of covered here. Moving a magnet toward or away from the coil. Again, if you move one with respect to another, it's going to cause that magnetic field to change because you're going to have, again, as you move it closer, a stronger field. As you move it farther away, a weaker field. And the lines of those field lines are going to intersect those wires at different places and different numbers of them as you're moving it. And that's what's going to give you that electromotive force. Moving the coil into or out of the magnetic field. So you don't have to move the magnet. You could move the coil instead. As long as they're moving with respect to one another, you're going to get that induction of current in your wire. Rotating the coil relative to the magnet. Okay, if you rotate the coil, and again, you have to think about what we talked about the other day about if you have your current flow like parallel to your field, that's not going to do anything. But if you rotate it about an axis that's perpendicular to your field, then yes, you're going to, or perpendicular to your flow, whatever, then yes, you're going to get an induction there as well. Okay, so again, it's all about moving these with respect to one another in a way that changes the magnetic flux, or the number of the magnetic field lines that penetrate the wire. And that's what gives you this electromotive force, or EMF, and that's what causes the electrons to move and form a current. Again, you can open this on your own screen if I'm going too fast. This is currently slide 69. All right, so let's talk about Faraday's experiment, because he referenced that in the video, and you saw, you did see one of Faraday's experiments, but this is actually the first one that he did. And what he did was he wound a thick iron ring on both sides with insulated wire. One end was connected to a battery, and it's shown here in this picture. Here's the battery. Here's that wire wound around this ring. The other side was connected to a galvanometer, or ammeter, but something that was able to measure the current. Now the wire is insulated, and that means that there is no direct connection between this side and this side. So when he turns this thing on and completes the circuit, now you have the flow of electricity through these wires and through this coil on the left-hand side. And we already know that the flow of charge generates a magnetic field. So even though these wires aren't directly connected to each other, the magnetic field that was generated by this coil of wire on the left-hand side would penetrate this coil of wire on the right-hand side. And when that field changes, like when he flips the switch on or when he flips the switch off, he was able to pick up a reading of current on this device over here. So even though they weren't directly connected, this device is not connected to the battery, he was able to see that current was generated or started to move in the wire anyway. And it was due to the magnetic field created by the current over here. So this field induced a current here. That's why it's called electromagnetic induction. But it says right here that he only observed the galvanometer reading when the switch was turned on and when it was turned off. And that's because that's when you have a change in the field, is when you turn the switch on or when you turn the switch off. Otherwise, it's just going to be constant the whole time. Okay, so that was his first experiment. And so he repeated that experiment using a permanent magnet, which is what we just saw in the video clip, and discovered that when a permanent magnet was moved in and out of a coil, that a current was induced in a coil, and that it is the change in the magnetic field with the turns of the coil that produce the current. Again, we looked at that in the video as well. Faraday summarized his findings saying that the magnitude of current was dependent upon the number of lines of force cut by the conductor in unit time. He's referring there to the magnetic flux. We're using that term quite a bit, but you're really not responsible for knowing it. But it has to do with the number of magnetic field lines that are actually penetrating the wire. Okay, and the change in that per unit time is what's generating that current flow. All right, so here's different factors that are going to affect your electromagnetic induction, and you definitely need to write these down. You are responsible for knowing these. You will see them again. Okay, these are also the same factors that you tested in the PhET and in the gizmo in the assignment on Monday. Okay, so the first factor that affected your electromagnetic induction was the direction of the magnet's motion. When you used the PhET and you moved the magnet toward the loop of wire, that caused a current flow in one direction, and when you moved it away, it caused a current flow in the other direction. You also just saw that in the video clip. His galvanometer pinged a point on the positive side one way and on the negative side the other way. You also saw something similar when the magnet was flipped around. So inserting the north pole of the magnet has an opposite effect as inserting a south pole of that same magnet would. It caused current flow in the opposite direction. So that's one factor that affects the electromagnetic induction, is the direction of the magnet's motion. The second factor is the separation between the magnetic field and the wire loop. You obviously are going to have more field lines penetrating your wire loop if your magnet is closer. And so that means you're going to have a stronger current, and that's what it says here. The effect of the magnetic field is greater when the two are closer to each other. The next factor that you looked at was the relative speed of the magnet or magnetic field. Again, you were able to test this in both of the simulations. But if you moved the magnet quickly, then the change in field lines cutting through the wire happened quickly as well, and it caused more current to flow. Whereas if you moved it slowly, then you got much less current, especially if it was really slow. Okay, so moving the magnet faster generates a greater current. Of course, that does mean slower would generate a smaller current. And then the last thing that you tested was the number of loops in the coil of wire. He tested that in a video as well, but it was something you looked at in the PhET. But if you had more loops, you were able to generate greater current than if you had fewer loops. By the way, you might want to add this term to your notes as well. This coil of wire that it's referring to has another name. It is called a solenoid. So if you see the term solenoid, it simply refers to a coil of wire. So if you have a bunch of wire wound in a coil like that, it is also called a solenoid. So that's just another vocabulary term that you should add to your notes. All right, so those are the ones that you tested, but you could change a bunch of different things. Those are the primary ones that you're responsible for knowing, though. But if you cause a change in the magnetic field, either by moving the wire or by moving a magnet or by rotating it, whatever, okay, or doing it faster or slower, all of those things are going to have an effect on the amount of current or the direction of the current that is induced in the wire. All right, so let's go ahead and write down our next definition, and that is going to be for an electromagnet. An electromagnet is going to utilize some of these same principles that we were just talking about, but an electromagnet is going to be formed when an electric current flows in a wire and creates a magnetic field around the wire. If you coil the wire into a solenoid, then you can create an electromagnet that strengthens the magnetic field. Okay, so a single piece of wire doesn't have much of a field. It does have a field. We know that. We did the right-hand rule. A wire carrying current has a magnetic field around it. But if you coil that wire so that you have multiple loops of it all next to each other in a row, now that magnetic field is building and adding, and each loop that you add adds more field strength. And I'm going to show you a video of this as well. But these electromagnets are going to be stronger when your coil is wrapped around an iron core. Okay, and that's because, yes, the wire does generate an a magnetic field. However, it's still not as strong unless you strengthen it by adding something like a magnetic core. If you put a nail or a bolt or just some kind of iron rod in the middle of your electromagnet, then now it's not just the field created by the current in the wire, but also that field is going to cause the domains to align in that material, and it's going to act more like a permanent magnet would. The coil has more loops. Again, as you add more windings or more turns of wire, you're building more and more of a field because they're adding to each other. And then if you have a greater current going through that coil, that's also going to generate more of a magnetic field. And you're going to get that by increasing your battery voltage or things like that. Okay, so again, notes for electromagnets. I'm going to show you a video clip about electromagnets now that's going to go over these different factors that we just talked about and how you can make one. In fact, you could do this at home if you wanted to.
Hi, this is Ben Finio with Science Buddies, and if you want to know what an electromagnet is
I'm hoping this thing decides to work better than that.
and how they work, then
She's been doing this all day. Why is the sound not working?
this video is for you. You might already know about regular magnets. They have opposite poles that attract, similar poles that repel, and they can even attract other metal objects that don't attract each other, like these paper clips. You can also take a compass, which is itself a small magnet, and move it around near another magnet, and the needle will point in the direction of the magnetic field. So how does a coil of wire manage to behave the same way? It turns out that moving electrical charge, or current, creates a magnetic field. Watch what happens when I connect this piece of wire to a battery. It makes the compass needle move just like a magnet did, so we know the wire must be creating a magnetic field. This magnetic field takes a circular shape around the wire like this. However, the magnetic field around a single straight wire is very weak, not enough to pick up even one of these paper clips. You can make the magnetic field much stronger by wrapping the wire into a coil called a solenoid. This causes the fields around each individual turn of wire to add up to make a much stronger, more uniform magnetic field similar to that of a bar magnet like this. However, you'll see that this coil of wire is still too weak to pick up an individual paperclip. To make an electromagnet really strong, you need to add a ferromagnetic core like this iron bolt. Ferromagnetic materials have many smaller individual magnetic domains. Normally, these domains are aligned randomly and cancel each other out. However, in the presence of an external magnetic field, these domains align with each other and the external field, making the overall field much stronger. Watch what happens when I insert this iron bolt into the core of my electromagnet. Now it's finally strong enough to pick up a paperclip. Unlike a regular magnet, an electromagnet can be turned on and off by removing the flow of electrical current. If you reverse the direction of the electric current, you reverse the direction of the magnetic field. To change the strength of an electromagnet, you can change the number of turns in the coil, the length of the coil, the amount of current flowing through the coil, or the core material, all of which would make a great science project. Because they have very low resistance, the wires in electromagnets can get very hot, so you should always disconnect them when not in use. The paper electromagnet in this video was just for a demonstration, but you should not try this at home because the paper could actually catch on fire. To see a variety of science.
Yeah, so if you do try to build one at home, you definitely don't put paper core in the middle of it because he is right. It will get pretty hot, especially if you're using a larger battery, and that could cause the paper to catch on fire. So iron core is great though. So put a bolt in there or a nail in there. If you have another ferromagnetic material, those work too, but iron's going to work the best. Okay, so you could use nickel or cobalt, but iron's going to give you the strongest electromagnet. So again, this is what's happening if we use, if we take a look at this wire right here that's wrapped around the nail, you have a generation of a magnetic field. And again, you can figure out which way it goes using the right-hand rule. Okay, because we basically have a whole bunch of circles of wire that are all on top of each other. And so like if you look at this image here, it says that the current's flowing in at the bottom. Okay, and you have this loop of wire. that it's flowing through, and then it goes to another loop, and they're all kind of stacked on top of each other. They're connected to each other. But if you use the right-hand rule, then you know that the current is flowing in at this end, and you can use the right-hand rule to figure out the field that it generates. And if I imagine holding the front of this loop, okay, then I know that my field is going to come up out of the center, and then it's going to curl back down on this side. And that's exactly what you see here. It comes up out of the center and then curls around. But it's a stack of these, and so each of those is building on the other one. And you get this strengthened field. And then if you put a core in there, then that field can help orient the domains of the atoms inside of that nail or that bolt or whatever. That's the nail in the picture. And that's going to strengthen it further, and it's going to act like a permanent magnet once you have that core in there. Okay, and this one is one you can turn on and off, just like you showed in the video clip, because if you stop the current, then you're going to stop this field. But again, you do need to know about electromagnets and the factors that are going to affect their strength. The next thing we need to talk about are transformers. Okay, so transformers are going to be devices that utilize electromagnetic induction to change the voltage. And so you have step-down transformers and step-up transformers, depending on whether you are changing the voltage to a higher voltage, that would be a step up, okay, it goes up, or a lower voltage, that would be a step down. And so they work in a similar way. It's just the way that they are constructed is kind of opposite each other. But a step-down transformer reduces voltage, and it will have fewer turns or loops on the secondary coil than it will on the primary coil. So the primary coil is where wherever your transformer is connected to the actual electricity source. And that is going to carry the voltage into the transformer on the primary coil side, and then it's going to flow through that coil, and it's going to induce a current in the secondary coil, even though they're not physically connected. Just like we looked at in the Faraday experiment earlier, it looks pretty similar to that. In that secondary coil, you're going to get the generation of, or induction of current, but if you have fewer windings on that coil, you're going to have less current than you started with. The opposite is also true. If you have fewer windings on the primary side and then more on the secondary side, then you're going to generate more voltage than you started with. And so you can use a transformer to step up or step down your voltage by means of electromagnetic induction. And I do have a video on this as well, but you do need to be able to identify them by image. If you look at the pictures, look at the number of loops on the primary and secondary. So your step down steps down the number of loops. It also steps down the voltage. Your step up, you step up the number of loops. You also step up your voltage. So it should be pretty easy to remember which one is which just by looking at the picture. And you should be able to remember what they do based on the name. So I said I had another video clip. So this is a video clip that's going to explain transformers a little bit more, and it has some good visuals. So I want you guys to watch this one.
Transformers are composed of an iron core ring wrapped in coils. One coil is connected to an AC input voltage and is called the primary coil. The other coil is connected to an output circuit with a load resistance and is called the secondary coil. The two coils are well insulated from each other and do not form a physical electrical connection. This gives a transformer its unique electricity altering properties. Transformers can either step up or step down a voltage. In a step-down transformer, the number of turns in the primary coil is greater than the number of turns in the secondary coil. In a step-up transformer, the number of turns in the secondary coil is greater than the number of turns in the primary coil. The constantly changing current driven by an alternating voltage source induces a changing magnetic field in the core of the transformer. The magnetic field created by the alternating current in the primary coil generates the flux in the transformer core. The secondary coil converts the flux back into current flow and produces a voltage at the load or resistance in the secondary circuit. If there are fewer coil turns on the secondary than on the primary, this is called a step-down transformer. The resulting voltage in the secondary circuit will be less than the primary. In this example, we have 20 turns on the primary coil and 10 turns on the secondary coil. To determine the decrease in voltage occurring in this step-down transformer, we can use a simple ratio formula.
This is the only
This
math you
formula
need.
simply states that the secondary voltage to primary voltage ratio is the same as the secondary coil to primary coil turn ratio. Rearranging the formula and then dividing 10 turns by 20 turns, we get 0.5 multiplied by 120V. This results in a calculated step-down voltage of 60 volts.
So you don't actually have to do it that way. Like if you have twice as many turns, you're going to get twice the voltage. If you have half as many turns, you're going to get half the voltage. That's what he just showed. So you need to know that proportional reasoning, but it's going to be direct. So the more turns you have, the more voltage you'll have, and vice versa. Okay, the next two devices that we need to talk about are a generator and a motor. You've heard me mention these, and they've been mentioned in the video clips as well. But a generator and motor have pretty much exactly opposite definitions. A generator is a device that converts mechanical energy into electrical energy, whereas a motor is a device that converts electrical energy into mechanical energy. You will have to remember those definitions, and you should be able to identify a generator and motor from a picture. Okay, I have some pictures up here, but in your generator, you're going to have something that has to physically be turned. It could be a crank that you turn. I don't know if you guys have ever seen them, but they sell flashlights with a crank on the end for like emergency situations where you can turn that crank and it will generate an electric current and be able to light that light bulb. Okay, or it could be like what you would see more at like a power plant. Instead of you turning a crank, it could be the wind turning the windmill, and then you're turning a turbine. Okay, so you're not doing anything. Or it could be water and like a hydroelectric dam, same thing. The water can turn that turbine that generates electricity. But that's what you have with the generator, is you take this mechanical energy, this turning motion that you get from either you physically turning something or the wind or the water or something physically turning something, and you use that to generate electricity. We looked at this the other day when we talked about if you applied a force to a loop of wire in a magnetic field, it would cause current to flow. Okay, we did that with our right-hand rule yesterday. Okay, a motor is the exact opposite situation. If you run that electric current through a loop of wire in a magnetic field, then you know that you're going to get a force on that wire. And we talked about, hey, what happens if I push here and pull here at the same time? And we talked about that rotation. That's what you have with a motor. If you run a current through that wire, then you're going to get forces that cause rotation of that wire loop, and that's how motors work. Okay, we're simplifying it down, but that's pretty much it. So when you look at a picture of a motor, you're going to see a battery. Okay, they're both going to have a loop of wire and a magnet, by the way. Both of them have that. Okay, but if you see a battery, that's a motor. It's using electricity to make motion. If you see a hand crank or some kind of like windmill, something that has to be turned by either you or the wind or the water, okay, then you know that you're looking at a generator that is going to convert that mechanical energy into electrical energy, and it's going to be used to power something like a light bulb. So you might see a picture like that. All right, so just to review some of this stuff real quick because we're pretty much done. A group of coiled wires we said was called a solenoid. 4 things that affect the strength of an electromagnet. You should already have these in your notes, but the number of loops or turns in your coil, the more of them you have, the stronger that electromagnet will be. The current flowing from your battery, the more current you have, the stronger that electromagnet will be. The core material, iron's going to make the best core, but any ferromagnetic material, which means iron, cobalt, or nickel, will make a suitable core. And then the core size. The larger the size, the stronger that electromagnet will be. Okay, so here's some pictures of electromagnets. Which of these would be stronger? Okay, you can see here 2 electromagnets both have a 9-volt battery. They both have the same number of loops of wire. The only difference is the core material. The one on the left is wrapped around a nail. The one on the right is wrapped around a pencil. So which one's going to be stronger? The one with the ferromagnetic core, so the one wrapped around the nail. Okay, similarly, we could look at these two. Okay, now I still have 9-volt batteries. These are both wrapped around nails, but my number of coils is different. Again, more coils will be stronger, so the stronger one on the bottom is the one on the right because there are more coils in that wire. So be able to answer questions like this about electromagnets. If you have a transformer question, be able to draw or recognize from a picture whether you're looking at a step-up or step-down transformer. This one says to draw a step-up transformer. That means I need to draw a transformer that has more loops or windings on the secondary side than the primary side, something like this. Okay, and when I draw it like that, I know also that it's going to step up my voltage, so I'm going to have more voltage on the output than on the input. You would use a transformer like this, a step-up transformer, if you were traveling abroad. Okay, really more so if they traveled here. Somebody from the UK comes here, their voltage that they have running through their homes over there is like 220 volts, and ours is 120. Okay, and so they would, if they plugged their hairdryer in here, assuming they had an adapter for the plug shape, they would also need a transformer so that they could step up the voltage to what is required by that device. Okay, you also have step-down transformers. We have those everywhere because the voltage in the power lines that carry the electricity to your neighborhood, not the same voltage in your house for a reason. That's really dangerous. And so there are transformers that step down that voltage so that it is more suitable for use in your home. Okay, so again, you'll see these in those type of situations. Here's the only math that you need. Okay, so this is the type of calculation that you need to be able to do. It says a portable X-ray unit has a step-up transformer, the 120 volt input of which is transformed to 120,000 volt output needed by the X-ray tube. The primary coil has 50 loops. What is the number of loops needed in the secondary coil? It's just a ratio. Okay, so if you are trying to go from 120 volts to 120,000 volts, if this one takes 50 loops, how many does this one take? You can just cross multiply and divide. Okay, and it would need 50,000 loops because if this is 1,000 times more voltage, this needs 1,000 times more loops. Okay, again, they're going to be proportional like that. So again, that's the only calculation we have, is just ratios. All right, so again, creates electricity is your generator. This is just reviewing some stuff. Here's those pictures I was talking about that you'll need to be able to identify. But that's it for the notes for this entire unit. Okay, so for the rest of the class period, you can work on the MyOpen Math assignment 1202.4, Electromagnetic Induction Problem Set. You do have a quiz tomorrow as well. If you're looking for additional practice, open up that unit summary. I am going to post a key to that later so that you can refer to that. And if you want to read more about motors, generators, transformers, and electromagnets, you can do that on the slides listed there. We're currently on slide 86, so starting on slide 87. Go ahead and get to work. If you have any questions for me, please let me know.